Our last talk for this session is by Calef and co-authors, and their talk is on spatial context for astronauts, spatial products, tools, and staff for human surface operations based on Mars in situ experience. Take it away.
Yeah, hi. This is Fred Calef. I'm going to present today, but I want to quickly acknowledge my co-authors, Hallie Gangala-Barca, who is a former MER Opportunity rover driver and now is the Instrument Data System Operations Lead. Tim Parker, who has localized every rover on the surface of Mars. Jeff Schroeder, who's doing mapping for Curiosity and Perseverance rover. Nathan Williams, who's worked landing site analysis for 2020, also worked on InSight. Heather Lethko has developed a series of data products that we use for 2020, as well as in the various Mars and Moontrek software. Laura Berger, who worked on InSight in the WebGIS. Bob Dean, who's worked in the Vickers software, developing ground data products, spatial data products, for all the MER rovers and the current rovers, Curiosity, Perseverance, and also working data for Heli, and Oleg Purser, who's also doing creating data products from orbital and converting them into meshes that we put into our rover driving software. And a name, very importantly, which I unfortunately did not put on this slide, is Tarek Solomon, who's developing our current and next generation web mapping software. Next slide, please. So today I'm going to go over all things mapping on our Mars surface missions. So I'm going to talk briefly about how our spatial products have been enhanced over the 2 decades now of near 2 decades of continuous surface operations on Mars, new operations and mapping tools that we're using, support that we provide for science and engineering, and then how this could be integrated into Lunar and Artemis surface missions. And just again to emphasize, we've driven over 24.5 kilometers with Curiosity. The Opportunity mission drove over 45 kilometers and lasted 14 years. We have over a marathon of distance we've driven, and again, nearly 2 decades of experience. And that's what I'm going to try to pull information in this talk from. Next slide, please. In terms of data products, the evolution of, when we landed like Viking in the 70s and even Pathfinder, we're talking about data that was in the kilometers per pixel scale. The surface was kind of a mystery. We had vague ideas from infrared thermal data about kind of rock density, but the surface was really a mystery. And I'm talking about the surface at the meter scale, at the decimeter scale, the centimeter scale. Even in the 2000s, when the MER rovers landed, we were still talking about meters per pixel, which is great. You certainly get that now a very much closer context, but you can't see the real hazards. Not all of them, not the ones that could actually halt your mission. Now with MSL and Perseverance, we have 25 centimeter per pixel visible orthophotos. We have 1 meter per pixel DEMS, and then a variety of scales moving up for that. We have multispectral data at 18 meters per pixel. So we can start to do science and surface operations at the level of the spacecraft themselves. Now, thankfully, co-respective with the increase in resolution at Mars, we also have the increasing resolution at the Moon. And I just listing the most recent spacecraft that I think we get the most data from, our important data from, is LRO, and a bunch of instruments there. But more importantly, the visible images where they're the LROC NAC cameras, which are getting orthophotos at 0.5 meters per pixel and 1.5 meter per pixel DEMS, and also a very nice global data set. So we can kind of translate what we've done on Mars straight to using it with lunar data. Next slide, please. So I can't reflect everything I heard in the previous talks is almost exactly what I'm going to say today. You should have been mapping yesterday. You should be mapping now, and it starts with landing site selection. So we use all those data products: thermal, dust cover, elevation, and then just our our ability of the vehicle to land in certain areas. And, let the scientists pick all the targets they want, and then the engineering drives which of those science targets are viable, and then we go through the whole science selection process. And it is an iterative process to get down to various places. Next slide, please. And again, this kind of tracks the data, but we've gone from a very manual georeference. We're around here, we did have about 30 mirror, some high resolution 30 mirror per pixel data when we landed Pathfinder and Sojourner back in 1997, 98. But then, we rapidly went to meters per pixel, then Curiosity centimeters, 25 centimeters per pixel over almost the whole landing site, including our eventual science areas that we're going to traverse to. And now with Perseverance, we're now same data sets, but now the georeferencing is automated, and we just have by correcting camera lenses, we get a higher level of processing of the data, and so it's much more accurate. Let me just remind you, yesterday, a week ago now, Perseverance landed with its landing vision system and landed with the reported the coordinate that was reported by the landing visual system was within 5 meters of actual that we verified on the ground. So we're becoming incredibly accurate in knowing exactly where we are immediately on the day. I transmitted that information within 5 minutes of landing. So accuracy has become incredibly important. It's always incredibly important, but we can do it in a very short time period. Next slide, please. So I have a lot of maps. I'm just going to go through them quickly, but just get the idea that, you can be mapping data from orbit, saying, what are the old images that we have and where the new images are coming along. A lot of stuff from Curiosity, and I'm really thankful for Ashwin for setting up this talk about science operations. So here's a map that's showing our actual traverse on a certain sol, and then as well as a strategic traverse on the right-hand side of the screen. Context names for scientists, Bar Harbor Quad, the sol that we're working on, and showing the positions. Very important to have this spatial context day-to-day for science operations to make everything efficient. Next slide. Similarly, keeping track of science observations. Here are all the drill holes for Curiosity up to Sol 1495, something like that. There are, there's a little thumbnail of the drill locations. There are the actual locations on the ground. Again, providing this context, keeping track of samples as we go. On the right-hand side, these contour lines, the light blue contour lines on the right, are every 25 meters in elevation, and that was kind of the cadence that we wanted to make sure that we stopped and perhaps either drill a sample or did an intensive investigation. So again, this is like taking the science part, how often do we want to sample, and committing that to engineering operations. Hey, rover drivers, when you get here, stop, and we need to do some science. Okay, next slide, please. So scales at all levels, right? So on the right-hand side, we have a bunch of geology that we've mapped together, and this went into a science publication. On the left is the kind of very, what I would call the tactical daily maps. Like here, this shows, here are the targets that we did with the rover. And importantly, we're linking together 3 different views: the orbital view kind of in the upper right-hand side, and then the in situ view from both a map perspective and an in situ perspective at the bottom of that slide. So it's, so we get all those contexts, not just from orbit, but 2D, 3D, and in situ oblique, again, for communicating where we were, what we did, and then linking that to analysis. Next slide, please. And this is, I just want to highlight this work for MER by Larry Crumpler. Again, mapping at the rover scale, at the mission traverse scale, all the geology around you, keeping track of geologic units, operational days that we were at locations, and then names that are corresponding to different mapping efforts, and then of course geologic models that pull out of that. So then when we move to the next location, what do we see? Next slide, please. Okay, again, keeping track of targets real time on the ground. Next slide. So part of this is about knowing where your instruments are. So we actually have tools which take the instrument angles and azimuths and elevations and puts them into points on the ground, so we can get that mapping context. Next slide. And again, we want to know where all these instruments have taken observations so that we have cross-instrument comparison. You increase your science by doing that. Next slide. And that'd be science down to, in our case, the millimeter. Here are a bunch of all these science targets that we've kept tracked and then divided by instrument types, and well as the days in which they were taken. Next slide. And so we've gone from those. We've evolved from very static maps to actually interactive maps, and I'm the PI on this multi-mission geographic information system where we have web-based mapping and I'll call it near real time or in real time, that when the data comes down, we process it, we localize where these instruments are, where the observations were, and not only that, but we can link them to actual science data products so that we can make decisions. We can make examples for like this target, the Tarn, I see a high calcium oxide value. Is that the same or different from yesterday, or where else have we seen values that are this high? So you can start to increase the spatial awareness of science observations and where where they occurred, and what is the spatial context is. Often the next question after, hey, this is an interesting result, the next question is, where is it? And this helps answer that question so we can make the next science discussion or decision, operational decision, stay here, collect more samples, or no, we've seen this, move on. Next slide, please.
We'll need to wrap up soon for questions.
Okay. Yep. Okay. Skip this slide. Just more mapping and context. Next slide. Next slide. Next slide. Next slide. We did this for insight, so we were able to do real-time positioning. Okay, so history mapping. I'll just say briefly. Yeah, this is fine. Just stay here. So fundamentals. Mapping before you land. Mapping goes from EDL to surface operations to EDL again. It's a full loop. You constantly do this. Maps are important for science teams to commit what they want to sample in terms of engineering. We need to have common mapping bases and coordinate systems. We need shared tools and spatial data so that people aren't working on two different locations, working in the same location, but not really being able to overlap their observations. And to do this, you need full-time mapping support. You need people who can communicate with the scientists and engineers. I'm a geologist by training, but I also perform these engineering operations of helping locate where science occurred and where we want it to occur. Next slide. So I think as people have said, EVAs are going to be like somewhere, it's going to be on the range of hours. This isn't really much different from how mission operations work, so that you can plan while astronauts are resting, and then have, be ready for them what to do the next EVA. So we should have a dedicated mapping team, both for strategic planning for the next day or the week, and then the day-to-day tactical operations. And that the spatial awareness, besides providing science information and tracking of samples, but provides a certain amount of safety and efficiency on the surface, so that everyone knows where we are, what has happened, and what we're going to do. Okay, thank you.
Great, thank you so much for that.